Good morning. This is Jeff Hammond, Executive Director at International Ground Source Heat Pump Association. Welcome to our July Dig Deeper webinar. We're thrilled to have Daniel Booy as our presenter, which I'll announce him shortly. Before we get started, I have just a few updates on what's going on with IGSHPA. So in the latest IGSHPA news, as you've probably seen, our Town Hall and Dig Deeper webinars are listed on the events and training page at IGSHPA.org. If you go there, you can submit abstracts for 2024. We do have all of the 2023 Town Halls and Dig Deepers set up, but we're still looking for topics for 2024. And it's always great to hear about new technologies and the latest updates. So feel free to go to IGSHPA.org for that. We started at the beginning of this year with sponsorships for these Town Hall and Dig Deeper webinars, and we do still have some openings for this year as well as next year, if you'd like to check those out. Updates on the conference. You may have seen emails. Registration is open now. We have already quite a few exhibitors, and we have most of our sponsorships filled up. We do have some advertising opportunities, but those are also filling up quickly. So you'll want to act on that at IGSHPA.org. These are the sponsors we have so far. We certainly couldn't do this conference without our generous sponsors. As you can see, we have one bronze sponsor, one silver sponsor, and the diamond left. All the others are filled, which is great. And we certainly appreciate the support of the sponsors. We're looking forward to another great conference this year. We're partnering again with the National Groundwater Association for that conference in December, and all the information is at IGSHPA.org. These are the exhibitors we have so far. We continue to add more and more each week. You can see the way this is set up. There's an entrance right here, and there's an entrance over here. So we're in a great location this year, actually the same location we had last year, but one of the differences is the side doors open at the same time as the front doors this year. So the NGWA has changed that. So as soon as you enter the exhibit area on Wednesday, you'll go right into the IGSHPA pavilion. So we're thrilled about that. As far as the program guide goes, this is something that will be passed out at the conference. We have quarter, half, and full page ads available. We do still have the inside cover and the back cover available. It's also in that same location, IGSHPA.org, at the conference link. The agenda is online. If you haven't seen that yet, we have 11 tracks this year. So each of the 3 days have some different tracks. We had a lot of participation, 76 submissions for speakers, and we ended up selecting 49 of those, as well as our annual general meeting, our leadership address, and the welcome reception. We also have some joint workshops with NGWA this year. So it's a really packed agenda. Our keynote is Alejandro Moreno, who's the Acting Secretary, Assistant Secretary for Energy Efficiency and Renewable Energy at the U.S. Department of Energy. And that was announced, I think, last week. So we are really excited to hear from Alejandro. He works with not only the Geothermal Technologies Office, but the other offices at Department of Energy. So we're really anxious to hear what he has to say about our industry. Our next research conference is in Montreal in 2024. We just opened abstracts, and those will be accepted until September 18th. So this is a little bit different than our annual conference. Last year, we had a combination of an annual conference and a research conference. The next research conference is separate, and then we'll probably look at combining those again, maybe every other year. We still aren't sure exactly how the research conference track will work, but this next one is in Montreal in 2024. Once those abstracts are reviewed, authors would be notified, and then they'll be able to submit papers which are reviewed by a peer review committee. If you're looking for continuing education credits for your IGSHPA certification, make sure that in the chat you send your name and email address, and we'll keep track of those. That will send out certificates at each half CEU interval. So those count towards your IGSHPA certification, all of the town halls and Dig Deeper webinars. We have a new feature starting with this one. and that is you can qualify for CEUs by watching recorded webinars. So for July, if you happen to be watching this recording rather than attending live, simply send this code into info@igshpa.org, and this will count as part of your CEU requirements. So from now on, each of these town halls and Dig Deepers will have a specific code that you can use for CEUs. Just a little housekeeping. If you would, please submit your questions in the chat, and I will read those at the end of Daniel's presentation. If we don't get to all the messages, we'll do our best to contact you and get those questions answered. Just out of courtesy, please mute your microphone unless you're speaking. And as a reminder, we are recording this session for viewing later. It's usually online about 2 to 3 days after the webinar. So by the beginning of the week, you should see this online. Go to igshpa.org. There's a YouTube icon at the very top. If you click on that, you will find the recording for this webinar. And one more slide before I introduce our speaker. Just a disclaimer and potential conflict of interest message. The upcoming presentation represents the opinion of the presenter and does not represent any official position, opinion, or endorsement of any products or services by IGSHPA or its members. IGSHPA Town Halls and Dig Deeper webinars are for member updates and education on the latest information in the geothermal heat pump industry and are not meant to endorse one technology or brand over another. It is a presenter's responsibility to disclose any conflict of interest or position that may arise in the content of the webinar. Excuse me. So it's my pleasure to introduce Daniel Booy. Believing that renewable energy systems are key to a sustainable future, Daniel began studying mechanical engineering in 1997 with specializations in thermodynamics and heat and mass transfer. He then launched Altum Engineering in 2007. Daniel's mission is to ensure that renewable energy systems function to their fullest potential. He's a geoexchange specialist with a focus on optimization of renewable energy systems and has been working in the geoexchange field since 2000. Daniel pairs cutting-edge technology with decades of hands-on experience in challenging projects. So we're excited to hear from Daniel for our Dig Deeper webinar. Thanks, Daniel, for presenting.
Thanks for the intro. All right. Potential conflict of interest. I guess I design and build systems and do controls all the time. So a lot of my opinions here are based on what I sell. And so just to disclose that. So take my opinions as you like based on that. I've unbranded this entire thing. If there's any branding left in here, it's not my intent. My intent is to be generic with brands. With that said, I'll get going here. So can you see this banner at the top?
No, I don't see the banner. That's
okay, cool. So that's just
showing up.
Okay,
just on yours.
All right. So the outline, first we're going to start with a presentation of an example system to guide the presentation, and an introduction of the 3 building side subsystems that we tend to use: sensible heating and cooling with radiant, humidity control separate from the radiant system, and ventilation separate from the radiant system. Then we'll go into an introduction of modern controls in the context of the example system. Some of it might be overly simplified for people, but I'll run through it pretty quick anyways. You can review it if you need to. The third thing will outline the radiant design process flowchart in a simple way, really simple and quick. The fourth thing, do detailed descriptions of handy template documents for managing design and construction of radiant heating and cooling systems based on my experience designing, building, commissioning these things, programming them. And next we'll go into the explanation of control algorithms in the context of the example system. And then conclusions and a summary and a question and answer period. I'm going to try to blast through this pretty quick. So I would like to take questions and answer questions and field comments and things at the end. So I've put the page numbers on here so we can go back to the page. If you note the page in your question or whatever, we can blast back to it. So learning objectives after attending this webinar. It's our intent that students will be able to design simple and cost-effective radiant heating and cooling systems, As my friend and mentor colleague Steve Kavanaugh says, keep it simple and solid. He's always had that sort of motto and everything. Second, understand the basics of modern control systems. There's a lot of, I feel, misnomers and misconceptions about modern control systems being overly complex and expensive, and they do not need to be. The older stuff is actually worse to use, in my opinion. Produce handy documentation to assist with the design and construction management of radiant heating and cooling systems, and then develop a simple sequence of operations for radiant heating and cooling system, or a radiant heating and cooling system. So the example system here, we've got on the left, this is all about the distribution system inside the building. We're not talking really about the ground heat exchanger. So I've left that off the diagram to make it bigger. So we've got the heat pump here on the left, and up at top, we've got a standard domestic hot water preheat system and going into a top-up tank. And the example system, these were both electric tanks that we used, all plastic construction tanks. I almost said the name of them there. And then we've got a buffer tank in this system with electric backup heat and top-up heat. Is where I am in British Columbia. It's fairly low carbon electricity and not super expensive. So that was a really easy way to get our backup heating. And then we've got pump 3 here, which goes to fan coils and fan coil system pressure bypass at the end of the line. And then pump 4 has a modulating 3-way valve to mix the radiant fluid as it comes back. And in heating mode, if we have the tank a little bit higher temperature for the fan coils, we can provide a lower temperature to the radiant floor. And in cooling, if we're doing dehumidification with the fan coils, we can keep the radiant supply water temperature above the dew point in the space. So that's page 4 if we have to go back to it. So my general philosophy on seasonal changeover is to try to use it whenever possible. For concerns about when it's still heating season and a zone needs cooling, try to use shades and opening windows. For concerns about when it's cooling season and a zone needs heating, try to use opening windows just to heat up the space. If it's for some reason cold, it's more point 2 that we come across as a large concern, particularly for server rooms and things like that, where we have internal gains. For the zone of buildings, so doors separate zones that have different loads. That really helps with the radiant systems. If possible, do not overcomplicate the system by doing heating and cooling at the same time. If you do have to do that, if possible, use supplemental heating or cooling devices rather than 4-pipe systems. And try not to use the seasonal changeover in the same day kind of thing. What I've had a lot of success with is people using water to air heat pumps supplemental in the spaces that have unseasonal loads, like a server room in the winter time would need cooling. So, small water to water unit or water to air unit for that. And if you have to use like a 4-pipe system with 2 tanks and 3-way valves switching over, please go and see my New York Geo presentation for tips on what to do with those 4-pipe systems. Because I've come across a lot of control and piping problems and leaking from the heating and cooling sides in other people's systems when I come to fix them. So I talk about that quite a bit in that presentation. So if you do have to go there, then maybe check that out. 3 independent building side subsystems. So we've got the ventilation system, which would be a HRV or ERV, depending on humidity and climate. And then we typically will have in dry winter locations a humidifier for the heating season, and that'll be put into the HRV makeup air supplier. Strategic exhaust locations, like for instance, a lot of the reason why people are doing these systems is to have less ductwork and open concept ceilings with exposed beams and things like that, which means often atrium has a high roof or a great room has a high roof, and a lot of the heat sits up in the top of the in the winter time, particularly the heat sits up at the top. You want to get that back down from the top, and you can use one of your exhaust for the HRV or ERV to do that, and then destratify the air. Hydronic makeup air unit if makeup air is required. So a lot of people are still using gas makeup air units, which defeats the purpose of having a geothermal system in the building, in my opinion, particularly if you're bringing in -40 air. So on a recent job, I designed and built a hydronic makeup air unit because I couldn't find a decent one for sale at a effective price, an economical price. So we did all the controls for that, and it works quite well off of the hydronic system. It's built up. So yeah, if anyone knows of anything off the shelf that please let me know. But yeah, if you have to build one up, then it's not too hard to do as well. You can talk to me about that. I'll help you out with that. I went through about 3-4 days on site, commissioning that and perfecting the controls on it, because it was a tough thing to do first time. So then you've got your sensible heating and cooling system using radiant panels and using the fan coils for top up. And then thirdly, we have a latent heat removal or dehumidification using fan coils in the system. So introduction to the point types in a modern control system. We have digital inputs, which is when the controller reads a switch closure from another device. That's typically going to be a dry contact, which means there's no voltage being sent to the controller. So if the other device is sending out a voltage instead of a dry contact, we usually put a relay in between, so the controller is just seeing a dry contact, no voltage on a switch. We've got a digital output where the controller closes a switch to turn another device on and off by a relay. So that's typically we will be putting out a dry contact to another device, but sometimes with a heat pump, we'll take the electricity off of the heat pump's transformer, run it through the switch side of the relay, and then back to the heat pump Y1, Y2, or O terminal, or whatever it may be on there. Then we've got analog inputs, the third type, where a controller reads a sensor or valve position, for example. So that'll be all your temperature sensors and feedback from that three-way valve we saw on page 4. Then we've got analog outputs where the controller sends out a signal that's typically 0 to 10 volt DC in our systems, or 4 to 20 milliamps, to control a modulating device such as a three-way valve. So those are the 4 point types. And in the example system, the digital inputs and outputs that we have it's quite simple. We don't have a lot of them. We've got a seasonal mode selection switch, which is just a switch. That's a digital input, and that's to the controller off of a switch that we typically put on the control panel, but it could be remote up in the occupied space as well. And that's just so someone can turn the whole thing into heating or cooling mode. And then we've got a makeup tank alarm for I almost said the brand name, hydronic makeup tank, which pumps water into the system if the system gets low. I don't like to put city water as a direct makeup to any of my systems, because I've had the experience where a contractor I knew came back from Christmas break, and one of the pipes had frozen in one of the buildings that was sort of half done but still had water in it. And the city water went in and iced up the entire building. I guess the hoarding blew off and the heat wasn't running for the construction heat, and there was ice everywhere in the building. And I've seen also district energy systems with like 30 gallons per minute makeup water that didn't get noticed for about 5 years. And because the operators weren't really trained. And yeah, so that put a lot of iron into the system, oxygen in the system, corrosion. The makeup meter was hard to get to and hard to read. So that's why we have that. So the makeup tank alarm, because we have a smaller volume of water in the makeup tank than what we would have from the city, obviously. That will alarm if the system goes over pressure, if it is under pressure, or if the tank gets too low. So it's a pretty key part of our system. For digital outputs, we have a heat pump stage 1 in that system, heat pump stage 2, digital output 3, heat pump reversing valve for cooling, digital output 4, backup heater enable in that buffer tank. So that's just a dry contact. And digital output 5, we have a domestic hot water preheat tank contactor. So every week for about an hour, I think 2 hours, we will energize that contactor and let the preheat tank, which has its own electrical element, heat up the tank to the set point that's on that tank. And that sanitizes the preheat tank and keeps the water warm if the heat pump's not running. So if it's in a sort of a shoulder season or they're not using cooling in the summer, we don't have a whole bunch of stagnant water sitting there at room temperature, having Legionella add to it. And then, concern is if somebody fills a bathtub and uses up the top-up tank full of water, and then this Legionella water comes into the top-up tank, then someone else starts showering or whatever, might not have had enough residence time to kill the Legionella. It might be a hazard. So, and it also gives us twice the volume of domestic hot water. If the desuperheater is not doing the job off of the heat pump, we still have our volume of stored water that the client paid for in those 2 tanks. So that's the digitals. Then we get into the analog inputs and outputs. So it's pretty simple. We've got buffer tank temperature input, a domestic hot water preheat tank temperature input, and a radiant supply water temperature input for controlling that radiant 3-way valve. And then we have one analog out, which is the radiant 3-way valve control. And in that system, it was an error to water system. So I put in this note so I'd remember to say there's some other points. But contact me after the presentation if you want to chat about air to water heat pump systems with passive G-frost if you're designing air to water heat pump systems, because like on the coast here when we use air to water heat pump systems, they're not very efficient compared to geo because they do a active defrost and they take energy out of the hydronic system and use compressor energy to do the defrost. But with this system, for the first time we're trying, and I'll find out this winter exactly how well it works because I only got to do it at 10 degrees C in the spring there when we finished up. So I'm excited to see it happen around 5 degrees C. We have a lot of 5 degrees C weather in our winter. So whenever it's above freezing, we're going to be cutting off the defrost cycle before it happens on the heat pump because we can read through BACnet MSTP. We can read the heat pump refrigerant pressure. And as that pressure starts to drop to the threshold where the heat pump would go into its defrost, we cut out the heat pump call and stop it from running. It turns off, then we have a separate wire a parallel wire going to the heat pump's fans, and we run the fan for a certain period of time at a certain speed on the outdoor unit to passively defrost the coil. And it worked really great at 10 degrees C. I'm going to see how it works closer to freezing, but the energy usage on those fans is really minimal. So it's a pretty neat thing for increasing air source heat pump efficiency by about double, maybe 1.5 times to double time, which is really significant. If this works globally, it has a huge significance. So pretty neat innovation there that I wanted to mention. If your clients don't go for geothermal and they're going to go for air source, then we've got a little bit of a fallback for you there. Okay, so introduction to the BACnet IP thermostats. So we started using BACnet IP thermostats quite some time ago, and there are 2 options out there. There's wireless versus wired. Wireless are great because you don't have people nicking wires in the walls of how a lot of people nick the Ethernet wires for the wired thermostats, and then we have to kind of try to trace it out while we're commissioning, and often the drywall's up at that point in time and painting's been done and things like that. So it's kind of hard to get into spaces and fix it. The wireless networks are prone to a little bit of, failure because the wireless comes in and out. So you got to be careful with the wireless ones to make sure that your network extends through the building at the mesh network, but the repeaters are working quite well on the jobs we have right now. So I'm fairly happy with the Wi-Fi, and I'm going away from the wired stats, other than to power them. We power them with 24 volts and run that back to the mechanical room and fuse the 24 volt lines so that we don't have batteries that need to be replaced in our thermostats. They also do relative humidity measurement, temperature measurement, and they take the set point input from the users and send that data to the controller. They output to the radiant zone valves on points on the thermostats. They input to read the zone valve end switches. So we're not running, we're running from in the zone to the manifold that's near the zone wires instead of home running all these wires back to the controller in the mechanical room. And we're not tying up points on the controller. We're putting those points that would be expensive on the controller onto less expensive thermostats that are needed anyways. And these thermostats these days look pretty good too. So, and people can log into them if they want to with their smartphones or whatever they want. So then we've got output to fan coil two-way valves to modulate them actually. So quite interesting, like we don't use balancing valves on the fan coils. In the summertime, the fan coils in the top of the valves serving the fan coils in the top of the building. In this example, it's a large home, it's a show home kind of thing. Probably I think $10 million budget or something like that on this place. So it's got open hallway or staircase all the way from the basement level up to the third level. And in the summertime, we're going to be opening our top level fan coils to 100%, those valves to 100%, and then we'll be throttling the lower level ones to 5% or whatever, and letting more water go through the ones that are higher up. And then we switch it when the system switched into heating mode. We put more flow into the fan coils that are at the bottom level. We also have a fan coil drain pan overflow sensor because these are trenched fan coils in this job. So we don't want those, that they have a fairly small freeboard in their drain pan. I think it's about 1 inch. And we don't want them overflowing and then causing all sorts of problems and then having it show up, one level down after it's soaked all the drywall out. So the owner wanted that and we put it in there. They didn't come with the trenched fan coils. We found another company that provided those, and then we put those in there custom. And then they also have occupancy and CO2 sensors on these thermostats. So you're getting a huge amount of information that you can then bring back through BACnet IP over the Wi-Fi to the controller without tying up points on the controller. So now you're using a fairly small controller, because if we look at this, the amount of points, we've only got 11 points. So it's a really small controller with a big brain to do all the coordination with the thermostats, and together they all work great. And we don't have a huge, massively expensive control system, but we still get really high-end heating and cooling with the radiant system. So the BACnet IP pumps that we're using for the radiant and the fan coil circuits are daisy chained with Cat5 or Cat6 Ethernet. So there's only one Ethernet line coming into the control panel. In bigger systems, you can just keep going like that. So it's a lot less wiring. And then it's all by BACnet. So you don't have a whole bunch of physical points tied up on a controller again. And we set them in the system for constant pressure. And we adjusted the bypasses with all the valves closed so that we had the bypasses opening enough when the pump's on minimum speed to get it to register flow, to come out of its low flow mode and actually have some flow to cool the seals and whatnot. So then anytime after that, it's only going to run when a valve is open. So it's going to be doing well. And the bypass is only opened as much as it has to be. So we won't be bypassing a lot of fluid. So This is pretty critical because it's a really simple system. I've seen systems like this have 40 pumps in them, and this has like what 5 pumps in total, including the recirc. So yeah, the idea of like pumping every radiant zone with a separate pump and having a 3-way valve that mixes the water onto it and balancing valves and all the rest. I've seen this a lot in a commercial environment. Nobody actually commissions them properly, and the pumps just are run continuously, and they're the first stage of heating, and the mechanical room's super hot. And yeah, it's a real waste of energy and fittings and pumps and wiring and all sorts of things, and it just gets way out of hand. So my philosophy is to keep it simple, and it works well. I think a lot of people who over design with the pumping and valves and everything have to spend a little bit more time in the mechanical room, seeing how hard it is to make it work and how much it doesn't work to get a wake up call. There's no real reason to have more pumps in the system than what I've shown on that diagram, unless you have more heat pumps and then you put a pump for each heat pump. But other than that, keep it simple, keep it cost effective, it'll work well. So then we enable the pumps using BACnet IP, and we only enable them when valve end switch is closed. And then we measure flow and use low flow logic in our controls to send out alarms so the pumps don't run deadheaded if there's a problem with a valve or something like that. And then we measure power consumption at the very beginning to detect system issues if as well as the flow. We've got that. So there's a lot of things in these pumps that you can read and do. We keep it pretty simple. So the radiant design process flow chart, really simplified here, is just to first off collect the owner's project requirements, what they want for zoning, coordinate with them, develop your zone diagrams, and then calculate zone by zone loads. Really important to have your zone by zone loads, so then you can have, you'll know if you have a zone with 4 loops in it, you'll know based on your delta T that you're looking for and your loads, you know what flow rate each of those loops has to have. And then you can sort of split up that flow rate based on which loops are on the outside of the building and which ones are on the inside. And then it'll preferentially heat the colder parts of the zone. So you need to know that on a zone by zone basis at the very beginning to be able to do that. After you've designed your radiant layout, which is the next step, and often that goes to a manufacturer and they'll do that for the designer, which is great. But if you give them your zone by zone loads to begin with, then they know what they're dealing with for flow rates and things like that too, so they can do their radiant layout. And then the final step is producing the coordination documents for the project. So those handy template documents I'm talking about are a zone list, a loop list, a points list, an electrical loads list, and a control system transformer loads list. And these are things that you want to develop very soon in the project. So I'm going to escape from here, go to the zone list here. Here's a zone list. So it's got, your zone or thermostat number. Then you've got your BACnet IP device ID, the rooms that are served, the room numbers off the drawings, because sometimes they have different names or whatever. And then we get the MAC address of the thermostat. So the IT people.
Pardon me, Daniel, I don't think we can see your list.
Oh, no.
Move that over to your other screen if you have 2 screens.
Okay. It's on the screen. I guess I have to.
You may have to unshare and reshare.
New share. Okay, zone descriptions. Here we go. Share my whole screen. Thought I'd done that. Can you see it now?
Yep.
Okay.
Okay. Thank you.
Okay. Thanks for that. Okay. So yeah, we've got the column A here was a zone number, thermostat number. Then we've got our BACnet IP device IDs here. And the rooms are served, the room numbers, MAC address, which is it's unique to every device actually. So that's important to have, because then you can read on the network. If you see what the MAC address is on the network, you know which device it is. IP address of the stat, two-way valves that are served by the stat for coordination, fan coils served by the stat, and then our comments. So that's the zone list, and it's helpful, handy tool. And on this job, I have the controller down here because again, it's MAC address. I still have to take from my notes the pump MAC addresses as well, but then we've also got some IP addresses here for those. And that's everything on the network. So then the next one was the loop list. So loop list is super handy because it tells everybody, you know, which valves are where and what zones they belong to. And for commissioning, it's super, super handy for being able to go and check that all these, like when you go to a thermostat and you turn up the heat, for instance, for the radiant heating, that the right loop valves pop up. And so we've got the numbering is like your zone dot manifold number dot loop number. So for instance, on like these first 7 are on manifold 1, and it says where manifold 1 is, what type of power head. I've removed that for the branding, the watts that the power head takes, and then the total watts for that manifold. So we can look at our next bit, which is getting into this. Is like, it looks really simple and oh yeah, why would you even need to do this? Well, it really, really helps. It's a super good checklist for commissioning. You send out the electrician or plumber, whoever's helping you out with this list, and they can go and check it out. And it's great for project documentation at closeout as well. So and we you know, I've found so many crossed over pipes or incorrect wiring using this list. It's amazing how much it catches. So, you know, yeah, it's really simple, but is very effective as well. So yeah, good document to have. Now the points list is typical of most projects, and we do some different things that are handy with the points list here. So we've got our point numbering, which is light here to make it better, but tipped over. So we got our point numbering, which is what controller it's on is 0, 1, controller number 1. What point it is on that controller is 0.1. And then this other stuff here is the actual numbering of the wires in the panel. So you can go to the panel drawing that has the wiring diagram for the panel and actually see what it is you're dealing with at that point. And that's really good for checking the electrician's work and coordinating the electrician as well, so that they can do the wiring. And then we've got the use, where it goes from, which controller it goes from, and where it goes to. And then we've got the signal type that it is, the make of the device or sensor, whatever it may be, the model, and our comments. And then we have progress notes for checking all this, our end-to-end checks and commissioning these points as we go through the project. So then, as we go further down, we get out of the physical points, and we get into the BACnet points. And so like, if you look at how much information we are exchanging with a thermostat, these could be physical points in another type of system. So just on one zone, we've got, you know, I'm going to just select 24 things that are happening. And some of them are to do workarounds on these thermostats to make them our slave and not use their own brain. But yeah, quite a few of them are. But you've got your, you know, your normal points like air temperature, humidity, temperature setback. There's a bunch of things in here that are would actually tie up points on a controller, but now they're being put off to a cheaper thermostat. and the wiring shortened, like I said before. So that's our points list. That's a super handy document to have. And if you use all that stuff, it coordinates it. And then by the end of the job, you've got all of your documentation in place. And then got the electrical loads list, which is a pretty typical document as well, but it's also handy for at the very beginning coordinating, like, do we have enough electric service in this building, particularly if it's a retrofit and it had a like natural gas boiler in it or something like that, right? So this I don't have to really go through. I'm sure you guys have all seen a million of these. So then we've got a really simple control transformer list, and bigger jobs this can get to be quite a big deal. So we add up all these loads and we know what size our transformer needs to be for in the control panel, and what our transformer needs to be for all the operating all the thermostats with their different loads on them, with their different zone valves and fan coil two-way valves and stuff like that. So it's just a place to organize your information and make sure you've got a big enough transformer, because if you don't, then you might not find out until it's the middle of winter and you're peaking. You might not find out during commissioning. So it's just a good check to have that thing together. Okay, cool. We're getting through this. All right. Okay. So what we do for tank zone temperature control. Okay, go away. The user has I want this banner to disappear. Should have practiced that part.
I think you can change that, Daniel, with the view options drop down. You can put it at the bottom of the screen, if I remember right.
Yeah. Okay. Zone control. So the user has control of how far a zone temperature has to be away from the set point before the zone valve is open. So I'm going to talk in heating mode just to make it simple. So let's say our set point is 21 degrees C, and it drops to, they have it set to drop a half a degree before it opens the zone valve. Now it's going to open the zone valve at 20.5 degrees, but now you've got all this energy going into the radiant panels and heating them up. So if you're using, the simplest way is to use the air temperature, but then by the time the air heats up to 21 degrees C, if you close your valve, then you've got all this additional energy in the slab that's going to come out of the slab, and or out of the floor, right, or ceiling or whatever, out of the panels. And that thermal mass has got the flywheel effect, and it's going to overshoot. So the user also has control of how far the zone temperature recovers before the zone valve closes. So typically we start with half of what the cut-in point is, so half of that band. So like, let's say it comes back a quarter degree, then we close that valve and then let the thermal mass come back up. Or if it's something that's a really high thermal mass basement, big thick slab or whatever, you might want to just do it like as soon as it comes up. So that helps with the overshoot that people experience with radiant systems. And then this, like I've said before, the zone valve end switches are used to enable the pump via the controller. The highest dew point in all zones dictates the minimum supply water temperature in cooling mode, so radiant pipes and panels do not sweat. If radiant cooling cannot keep up, the tank temperature drops to 45 degrees Fahrenheit or so, and the trench fan coils in that zone are started on minimum speed to bring up the dew point by dehumidifying the space. So the reason they start on minimum speed is so that they can fully cool the air below the dew point and then start sweating without blowing off the sweat off the coil, start dripping. And we want that to happen for quite some time before we start ramping up the fan. So then we slowly ramp up the fans if the space temperature continues to rise. So the two systems sort of work together, because if you've got a high dew point in the space, you're not going to be able to do too much radiant cooling, because your radiant cooling supply water temperature has to actually be pretty high. So you're not going to get a lot of capacity out of your radiant system. So then what that does is it puts more of the load on the fan coil once the fan coil starts, and lets it run for longer, which actually dehums the space, which works synergistically with the radiant, because once the space is dehummed, then the dew point goes down, and the supply water temperature from that three-way valve into the radiant system can go down as well. So they work together. And sometimes we need them, sometimes we don't, but it's a good idea to have them in there, at least in a central zone where a lot of humidity is being developed, in case you need it, because I fixed a fire hall recently that didn't have that. And when that heat dome happened 2 years ago here, we had no wind and high humidity and high temperatures, and we couldn't do any radiant cooling. So we absolutely needed something to bring the humidity down. And then they ended up just going to an air source heat pump, because it's too expensive to change all their radiant and all their pipes that were covered in the walls and everything. So at 19, we're doing pretty good. Okay. Fan coil fans ramp up if it continues to rise, and these fan coils are also used for fast or supplemental heating and cooling. So the user can put in like a fast heating mode, and if fast heating mode or fast cooling mode comes on, the fan coils are just going to come on to full, and the set point of the tank is going to go high for heating, or it's going to go cool for cooling. So yeah, that's like a neat mode for, like, if you're coming back from vacation, or you're occupying a building that's coming back from unoccupied time, then it can do a fast heat up, because it takes a while for the radiant to reply or to respond. So now the tank temperature control algorithm's quite interesting as well. What we do is we take the outdoor air temperature, and it's used to establish a tank reset temperature. But there's a user adjustable combination of trailing average and instantaneous outdoor air temperature, which is used to establish the reset temperature. So you can put a percentage weighting on the trailing average versus the instantaneous. And then the user adjustable trailing average time is used for response time tuning. So there's, higher thermal mass building leads to longer trailing average time required, and higher weighting on the trailing average outdoor temperature compared to the instantaneous outdoor air temperature. Now I've used the manufacturer that has the grooves in the plywood with a coating of metal on top of it for a low mass system. And in that case, we want to have a very, very short trailing average time. The building sort of reacts to the weather quicker. And we also have a little bit more weighting on the instantaneous outdoor air temperature. And then there's a user. So for efficiency and comfort, we have an algorithm that biases the reset, because the reset, if, like, you imagine in heating mode, you've got a reset that's set for a certain temperature, like maybe 90 degrees Fahrenheit going into the floor when it's cold out. But if that building's unoccupied and all the thermostats are set back to 50 degrees Fahrenheit, you don't need that temperature of water to heat the building. So this algorithm does some machine learning. It looks at, it has a user adjustable trailing average time for the percent open calculation of each radiant valve in the system. So for a high mass system, that adjustable trailing average time is longer, because things move slower. For a low mass system, it's shorter. And then we have a user adjustable valve percentage open checking frequency. So like this algorithm, how often does it check what the neediest zone valve percentage open is in that trailing time? So let's say it's an average trailing time of 1 hour. Well, you could be checking that every 10 minutes and see if it changes. It's a separate value. And then there's a threshold value as well. Let's say, okay, let's say in the last hour, on our 10-minute frequency, checking frequency, if in the last hour that the neediest zone valve is more than 75% open, then what we'll do is we'll say, okay, that's your 75% threshold. Then we'll bump up the tank temperature and heating, or we'll bump it down a little bit in cooling. And then, so that's the biasing, that's the machine learning. And then what it ends up doing is it ends up having the supply water temperature from the radiant as close to room temperature as possible, which increases the COP of the water-to-water units immensely. And also is comfortable. And then also provides, more steady control, less overshoot in the space, and that sort of thing. And then when you're in the shoulder season, if your system has, let's say you're going in heating mode, it's the morning, you need heating, and all of a sudden it's getting hot in the afternoon, okay, you want to switch it into cooling. Well, that algorithm will have, plus the reset, will have put the supply temperature to the radiant in heating mode just above room temperature. So then when you switch it later in the day, if you're going to do that, if you switch it to cooling, you're not cooling down the whole mass of the building and all the hydronics very far. So you're not wasting a bunch of energy. So that's how it all works together to optimize efficiency and human comfort, which is, it's quite a great deal. And you cannot do that with the standard systems that are bought off the shelf at plumbing wholesalers right now. They just don't do that. If they did do that, they'd be direct digital control systems, and they'd be the same thing as what's here. And if you tried to build that up with all the different components, which I have tried to do, it's very complex and it's very expensive and hard to deal with. So, there's a lot of benefits to this technology, including having all these points data logged and having remote access through the internet to be able to reprogram and check all these things and play with it. So then finally, at the end of this algorithm, some outer limits are applied to the max min reset temperature, just as a safety. So if someone, messes with it and they try to crank it, they can't. Got to keep it safe for the heat pump. So, in conclusion, summary, there are many advantages to having separate systems for sensible heating and cooling, ventilation, and humidity control. This is pretty standard knowledge in the industry right now. So I didn't get into all the advantages and disadvantages, but it's mainly we want to separate our ventilation from our heating and cooling. The modern controllers enable cost-effective high-end control compared to other options, and are essentially the same thing as a packaged controller. It's all consumer electronics. It's just that the modern direct digital controllers are they're coming down in price, and they're really good. They're amazing. I've worked with several brands now. The radiant system design flow chart is critical for avoiding rework and coordinating the project, catching errors as well. Handy template documents enable plumbers and electricians who are not experts in radiant heating and cooling to provide high-end systems at economical prices. That's a really, really key thing here, because we are using a lot of construction management projects or general contract projects or design build where we're just using the plumbers who are doing all the rest of the plumbing on the site, and we're using electricians who are doing all the rest of the electrical on site. And so we have a sheet metal scope for a sheet metal person who's doing the ERV HRV system separately, and these are all let out as separate contracts, but the handy template documents bring everybody together along with the design package that we deliver, which has got all the manuals in it, and we deliver that all at the beginning of the project before anyone constructs anything, so they have all the information available to them. And if they have a problem, they just call me up and I'm like, okay, go to this page in the manual, you find exactly what you need. And with decarbonization and moving away from traditional systems and into these more high-end systems that are very, very efficient, we have to train a huge amount of people. And so that's kind of why I wanted to do this presentation, is to show that, hey, like, we can do this with people who are already trained on plumbing and electrical, and not have to train a whole bunch of people. So like what I'll do is I'll design the thing, put together the design package and everything, and then provide the control system to these people. And then they do all the plumbing and the controls and wiring and everything. And then I come in, I do before commissioning, I do my end-to-end checks and inspections, and I train standard plumbers and electricians to do this. It doesn't take really, really high-tech people. So it actually reduces the scope of work on the controls person, me. Like if I had my own electrician, I would, be expensive, and it'd be another body on the site that doesn't need to be there because there's an electrician doing lights and plugs and stuff. So this is really, really big point here. Like we're trying to decarbonize the planet in a quick way and in an effective way. So we need to just supplement the skills of the people who are already out there instead of trying to, have it all done by refrigeration mechanics or people who are mechanical contractors who are skilled in all of these arts. We can, we use the refrigeration mechanic on the Sarda water system, but it was just to run the line sets and get us started up, put the refrigerant in. The rest of it was all done by typical people. I guess I'm rambling on about that a bit, but it's really important. Like we need to use the skills that are out there. Fifth point is that the control algorithms can be sophisticated and adjustable using modern controls, which is a key point. Okay, so now you guys can read this on your own, and while I'm taking some questions.
Thanks so much, Daniel. That was an exciting presentation. It's great to see you taking advantage of the latest technology. I love the, keep it simple approach, and those templates are really, really super helpful. So thanks for sharing with us. I want to be considerate of everybody's time. I'm showing 29 after the hour. Are you willing to stay around for some questions, Daniel?
Yeah, I'm really sorry. I thought that was going to take a lot less time.
No. Hey, it's great to have all this information. Okay. Don't be sorry. Is it okay if we do some questions, or would you like to follow up with those later?
People stay, and then if it grab my contact information if you've got to go, and I'm happy to answer questions later if people have questions as well offline. Okay. It's really cool stuff. So yeah, I totally want to help. Yeah.
Okay, very good. Well, then we'll just take a few here. Okay. Jackie asked the question, do you ever designate a main thermostat as the digital input 1 seasonal mode selection switch?
Yeah, you could do that. But actually with the thermostats we're using, you could just wire a standard light switch to it, or any type of toggle switch, like on-off switch, and just wire into one of the points on the thermostat. You wouldn't have to actually use a whole thermostat as a switch. But okay. Yeah, totally. Yeah, that's a great idea.
Thank you.
I should have done that so they don't have to go downstairs, because the guy this week when I talked to him, he's like, I got to go downstairs to switch this over. I'm like, yeah, well, you don't want to do it all the time. He's like, well, yeah, but I don't want to go downstairs. So that's great.
Very good.
Thank you for that. Yeah.
I'm going to skip ahead to Roger's question, and then we'll come back. He asked about the code for CEUs. That's just for people who are watching this recording. If you are live, just simply send a chat message with your name and email, and we'll make sure you get taken care of. I think you asked Jackie's other question. You're describing a zone valve system with a single pump being switched by the end switch from one or more of the zone valves, correct? Just making sure I understand. I believe you covered that already, but that is correct, I think.
Yeah, with the pressure bypass at the furthest part of the system, so that if the pressure bypass is activated, we have warm or chilled water throughout the whole system, ready for the zones, ready to be used. Particularly for fan coils, if you're going to turn on a fan coil, you want to have the right temperature of air coming out of it. Yeah, that's what we're doing.
All right, we'll take 2 questions from Victor, and then we'll wrap up. Victor asks, have you seen cases where the ground source heat pump runtime is controlled, for example, when coupled with the buffer tank, to reduce carbon emissions by changing when the equipment runs off of grid electricity?
Yeah, we're working on that right now.
Okay.
but the buffer tank doesn't do a huge amount of energy storage for that, off peak. The one I'm working on right now has like a huge solar array, and they can't put all the electricity back onto the grid. So they want us to crank the temperature of the swimming pool during the daytime and then let it relax during the nighttime. So to use, like, if we have excess electricity available off the solar array, we'll run the heat pumps and then heat up the swimming pool. And then we're also going to be on that project using discretionary zones. Like there's a few zones that will never be occupied. I just know it's just a huge place, and we'll be able to like overcool those in the daytime when the solar's abundant, or overheat them in the winter if the solar is abundant. And then let them drift when it's not abundant. So using the thermal mass of the building rather than the buffer, because there's so much more thermal mass in the concrete. The buffer tank's just for anti-short cycling of the heat pump, really. Yep. Okay. Next question. Hello.
Sorry about that. I lost my internet for just a second there.
Oh, that's okay.
Let me see here. If we had one more question from Victor. Yeah, let's see here. What is the smallest and largest?
Here, I can finish that. I think he froze a little bit. He asked, what's the smallest and largest buffer tank TES sizes you've seen installed when used as backup heat? And how many hours of peak load are you typically designing for?
Oh, the buffer tank's used for backup heat because it's got an electric element in it. It's an electric
buffer tank size you've seen installed when used as a
Oh,
backup.
sorry, Jeff.
Okay, yeah, so thanks, Jeff. So what we had there was that the buffer tank is just for anti-short cycling of the heat pump. It's not for thermal energy storage. If we were going to do thermal energy storage, we do it with a phase change material, and there are companies that are doing that with tunable phase change materials that have phase change at different temperatures. But we typically, and I also saw a comment about the solar thermal, Victor. It's not solar thermal, it's actually a PV array, and we're using electricity to run the heat pumps, and then we're turning that into thermal energy on the site instead of just not using the electricity that's available, because they have a 50 kilowatt PV array and they're only allowed to put 10 back onto the grid. So they're, we got to use that energy somewhere. So that's what that's about. So thermal energy storage outside of the tank. The only thermal energy storage for the tank is your 10 gallons per ton of your first stage, which that's what the buffer's for. It's absolutely not for thermal energy storage for off peak or anything like that. Because typically the tank will just drain, like the energy will drain out of the tank immediately. So I wouldn't waste the money on a big tank like that unless it's phase change thermal energy storage, and then you'd have to prove it out with your rates and your loads and get right into your load analysis for that to prove out the value of that. Next question, please.
Great discussions. Thank you so much, Daniel. And sorry for the technical difficulties here with connections, but hopefully we made it through, and we'll have this recording online here in the next few days. So everyone have a great weekend. Thanks so much, Daniel, for the presentation. And we'll see everyone at the next Dig Deeper or Town Hall webinar. Thanks so much.
Thanks, everybody, for coming. Thank you.